Hello everyone, this is part 2 of our series on graphing quadratic functions. In part 1 we learned how to graph a quadratic function given in vertex form. In this video we'll learn how to graph quadratic functions that are not provided in vertex form but rather given to us in standard form. We're also going to look at left-right, or also known as horizontal parabolas, and we'll also cover some applications toward the end. So we'll go right into it without any delay. If you recall, when we were dealing with linear or first degree equations, and they were not given to us in the most useful form, which we know is the slope-intercept form, and if, for example, they were given to us in standard form, we would take them and put them in this highly useful form, the slope-intercept form, and then proceed to graph them very efficiently. We're going to be doing exactly the same thing with parabolas. If the quadratic function is given to us in this standard form, we'll take this and we'll learn how to convert it to the vertex form, which we're already familiar with, and then we can quickly graph it by finding the 3 strategically important points that we've discussed in our previous video. And or we can also, once in vertex form, we can also do it by interpreting the various transformations to the graph of y equals x squared in order to obtain the given function's graph. So let's go ahead and take a look at how we're going to approach that. All right, so here we can see that we have a quadratic function given to us in standard form, and we're asked to find the vertex, the axis of symmetry, the domain, and the range. So the process is really simple as 1, 2, 3. So basically the first thing that I recommend is you go ahead and change the f of x to y, because we are going to be graphing the output values on the y-axis, and this also looks simpler and it's easier to keep rewriting y instead of f of x. It's really an optional step, but it's highly recommended. Then what we need to do is we're going to be using the method of completing the square again, which we've seen before, but in this case, like in all cases involving completing the square, we want to make sure that the coefficient of the square term is 1 before we proceed with completing the square. So the first thing you need to do is look for that coefficient, and if it's not 1, then we're gonna want to divide both sides by it to make it 1. So we notice here that this is 1, so we can go ahead and proceed with completing the square. So here we show the completing the square box on the side. This is always side work. It's not something you put in the middle of your process. And we take half the coefficient of the x term, which is 3 obviously, and then we square that to get 9. So normally when we do this with equations, we go ahead and add 9 on this side and immediately add it to the other side. But since we want to keep this simple and eventually get to this form, y equals a times x minus h squared plus k, we want to keep this side as is. So we'll use a different kind of trick. Instead of adding it to both sides, we'll add and subtract it from the same side, which notice that just basically is adding 0 to this equation, which is not going to change the overall expression. So but it does bring an important cosmetic change, which will help us put it in the proper format, because notice now over here we have a perfect square trinomial, and right there we have 2 like terms that we can combine. So if we go ahead and do that, we're going to write this in this form as we know, and these two, negative 9 plus 11, that'll just end up giving us plus 2. So very quickly we have taken a quadratic function given to us in standard form, and we have now written it in vertex form, which is extremely useful because now we know that if we compare that to our standard vertex form, we can see that our a is 1 right here, the coefficient. H, of course, if we write this in truly standard form, we would want to go one more step, but we usually don't do this. But if you want to, you could. If you write it as x minus -3 squared plus 2, now you can see it's completely in vertex form, which is x minus h. So you can see h, when there's a plus here, h actually ends up being -3 right there, which is there is the translation constant for our horizontal translation. And also we can see that k is 2. So we know that from our last section, that the last video, that hk is going to be the vertex. So once we have the vertex, we can really start our graph because we can create our table. Remember, we always start with the vertex in the middle, then we'll just go one horizontal unit to the left of that and one horizontal unit to the right of that. Then we go ahead and evaluate the expression at those points. Now, starting with the x value of the vertex, actually, we can just plug it in. -3 plus 3, that's 0, squared is 0, plus 2 gives us 2. That's where this comes from. So now we know where the vertex is. And plugging in -4, we get -4 plus 3, which is -1, squared is 1, plus 2 is 3. So that's where this 3 comes from. We do the same for -2. Even though we know because of symmetry is going to be the same, we always do it to make sure we didn't make an error on the -4 calculation. So -2 plus 3 is 1, squared is 1, plus 2 is 3, as we expected. This should happen because we're moving an exact same distance in both directions, and we know that graphs of parabolas are symmetric. So in this way we found our graph, and of course we know the vertex. We already said that it's -3, 2. The vertical line, imaginary line that splits a parabola exactly in half and reveals its symmetric nature, is going to be right there at x equals h, which in this case is -3. So that's the axis of symmetry. Make sure you don't just say -3, because that's not the equation of a line. When we say what's the equation of the axis of symmetry, we need the equation of a line. And x equals -3 is an equation of a vertical line. -3 by itself is just a real number. So make sure you give it in the proper format as x equals -3. Domain, of course, there's no x value that would get you into any kind of a trouble in a quadratic function like this. So the domain is the set of all real numbers. And as far as the set of outputs, notice they start here and go up. So we see right here that's y equals 2. Make sure we don't go with the x value. We want where the y's begin. Remember, y's begin at 2 and go up from there. So that's why the range is starting at 2 including 2. That's why we need the bracket, comma, infinity. In set builder notation, of course, the same range would be all y, such that y is greater than or equal to 2. Some people want to get a little bit more detailed, they may say y belonging to R. That means the set of real numbers such that y is greater than or equal to 2. So you may see any of these 3 of these forms for the range, and they're all correct. So make sure you understand and can handle a simple problem like this before we proceed. Alright, so here we have another example. This time we notice that the coefficient of x squared is not 1, so we go ahead and divide both sides by -3 to make it 1. On this side we end up with y over -3. Here that splits up, so we get -3 x squared over -3, which is just x squared. Positive 12x over -3, that gives us -4x. And then -16 over -3, which gives us positive 16 over 3. Now we go ahead and proceed with completing the square on x squared minus 4x. So here's the CTS box completing the square. So we take 1/2 the coefficient of x, which is -4, that gives us -2, and we go ahead and square it, and that gives us 4. So we need to add a 4, and remember, we like to take care of things on the same side, so we immediately subtract 4, and we don't forget the positive 16 over 3, which was already there. So rewriting the perfect square trinomial that we've created as its other form, as the square of a binomial, we get quantity x minus 2 squared minus, now I wrote the 4 here as 12 over 3 because I'm going to be wanting to combine it with 16 over 3. So finally we end up with y over -3 equals quantity x minus 2 squared plus 4/3. Now, of course, this dividing by -3 on the y side was temporary. Eventually we want to be in the form of y equals a times x minus h squared plus k. So now that we've taken care of business on the right side, we'll go ahead and multiply both sides by -3 to get rid of that on this side. So notice that this is what's happening. We're multiplying by -3 on this side and also on the other side, and of course remember we have to distribute, so each of these 1, 2, 3 terms is going to get multiplied by -3 because of distribution. So notice here the two -3's will cancel out, so you just get y and -3 times x minus 2 squared from here, and this positive times negative is going to give us a minus, and the 3's will cancel out, so we just get 4. So notice once again we took a quadratic function in standard form and very smoothly transformed it into the much more useful vertex form. So now in this form we can see that the coefficient a is -3. This is going to be h. Notice x minus h, so this is h itself. When there's a plus here we take the opposite, but when it's x minus 2 we know that's going to be h itself. The simplest way to think about it is whatever number you see after x, whether it's plus or minus, take its opposite and that'll be the value of h. So here you have a -2, so the opposite of that will be 2. If it were +2, you would take the opposite of that, which is -2 for h. So here h is 2 and k is -4. So we know that hk is going to be the vertex, and that's where we're going to start with our table. You always start in the middle with the vertex, then take the x value of the vertex and go 1 unit to the left of that and go 1 unit to the right of that to get the simplest 3 forms you can have to graph the parabola. So when we take 2 itself, we get 2 minus 2, which is 0 squared, gives us 0 times that is 0 minus 4 gives us -4. That's where this comes from. Then we take 1, so we have 1 minus 2, which is -1 squared is 1 times -3 is -3, minus 4 gives us -7. Then we try 3. Even though we think it's going to be -7, we're going to do it anyway to make sure we didn't make a mistake with -7. So we have 3 minus 2 is 1 squared is 1 times -3 is -3 minus 4 is -7. So we did it correctly, and that's all we need to graph the parabola. So we plot those 3 points and we smoothly graph the parabola through them. And of course the axis of symmetry is going to be x equals h. In this case h is 2, so it's going to be x equals 2. That's the equation of this vertical line that goes through x equals 2. And some analysis of A tells us that because A is negative, we knew this is going to be a downward facing parabola. The technical term for that is that it's concave down. And also the absolute value of A is 3, which means we know that means there's a vertical stretch, but horizontally that's going to look like a compression. So there's an actual narrowing effect in the horizontal direction, and that always happens when the absolute value of A is greater than 1. And the fact that it is negative, A itself, we know that means there's a vertical reflection with respect to this horizontal line that goes through the vertex. And if you wanted to describe the actions that need to occur to the graph of y equals x squared, which is our standard parabola, which sits right here where I'm pointing to, then you know that you would, looking at this, you realize you would need to take the graph of x squared, move it 2 units to the right because of this here. Then you would move it 4 units down because of that -4. Then you would make it narrower because of the 3 out here. And finally you would reflect it and vertically reflect it. And then you would have the exact same graph. So you can always do these graphs either using just points that you plot, or you can talk about the various transformations that need to occur to the graph of y equals x squared in order to obtain this graph. So make sure you can handle this on your own, and then we'll move on. All right, one of the things we need to understand about parabolas is, of course, you know that when you graph any parabola, such as that, now you know that there are going to be some places where it crosses the x-axis, possibly with the x. These would be called the Xintercepts, the places where it crosses the x-axis, and there's always one place where it will cross the y-axis. Now, this one is guaranteed. Every parabola that you graph will cross the y-axis, but these may not happen because let's show you a different parabola. For example, if we have, say, this parabola, notice this parabola would never cross the x-axis, would it? So it would not have any points of intersection with the x-axis, so it has no so-called x-intercepts. But notice it will eventually hit the y-axis. They all will. You will always have a y-intercept, and as you'll see in a minute, it's actually very easy to find. Now, when you look at the y-intercept, notice it's occurring when the x value is 0. So if you take this equation, which is the standard form of a parabola, and just replace x with 0, notice these two terms will always zero out, and you just get c. So c is going to be the y value of the y-intercept of any parabola in standard form. So the proper way of course, describing a point in the plane is using an ordered pair. So the y-intercept is actually the ordered pair 0c, which will be right there. And if a parabola does have x-intercepts, of course they will happen when y is 0. So if you want to find the y-intercepts, it's very easy. set y equals 0 and you'll get a quadratic equation, and you solve that, and that will give you the x coordinates of the x-intercept. Then you'll pair them with y values of 0 and you'll have your x-intercepts. Notice that one of our old friends, the discriminant, which we've discussed before, which is b squared minus 4ac, can be used to tell you how many x-intercepts a particular quadratic function's graph is going to have. The way that works is if b squared minus 4ac is greater than 0, meaning, if you think of the quadratic formula, the radicand of the quadratic formula, the expression under the radical, then that's going to give us 2 x-intercepts. And of course, the reason for that is because when that's the case, we know that this quadratic equation that's associated with setting the y value equals 0 is going to have 2 real solutions. Now, if it's 0, then we know that this equation, as we've discussed previously in a different video, is going to have 1 real double solution. So in this case, you're only going to get 1 x-intercept. And when it's negative, we know that it's never going to give us a real solution. We're going to get 2 complex conjugate solutions, which graphically speaking just means it's never going to cross the x-axis. So we'll look at some visuals in a minute. So here are some examples of possible number of x-intercepts. Notice in these 2 cases, both of these parabolas have 2 x-intercepts. These 2 graphs show parabolas that only cross the x-axis at one point. So as you can see, what that means is the vertex itself is going to be on the x-axis. That's the only way a parabola can have only 1 x-intercept. And here's a couple of graphs of parabolas which are not going to have any x-intercepts. Notice they never cross the x-axis. So as far as the possible number of x-intercepts, you either have 2, you have 1, or you have none. There are no other possibilities. You're never going to find a parabola that has 3 x-intercepts or anything like that. All right? Make sure you understand that, and then we'll proceed. So here we have a quadratic function that we want to find all the intercepts for. Of course, when we mean for this, we mean for the graph of this function, the parabola, and we want to do it without graphing. And then we're going to verify our results with a discriminant check, see if it agrees with that rule, and then we're going to display the results on a graphing calculator. So remember to find the y-intercept. We'll start with that. That's the easiest case. So to find the y-intercept, that's the place where the graph will cross the y-axis, and we know at that point we set x equal to 0 and solve for y. So we have 0 equals, let's fix that, we have y equals, remember, if you just replace f of x with y, you have y equals x squared plus 5x plus 6. So we get y equals 0 squared plus 5 times 0 plus 6. We already knew it's going to work out like that, where it becomes c. So y equals 6. So to write the y-intercept, we actually say the y-intercept is the ordered pair 0, 6. That's the proper way to present it. Now, for the x-intercepts, we do the opposite. for the x-intercepts, we're going to let y be 0 and solve for x. So remember, the equation is y equals x squared plus 5x plus 6. This time we're going to let y be 0. So we're going to get this equation, which we'll try to solve by factoring. If that doesn't work, we can use completing the square. If we don't feel like doing that, we could always do the quadratic formula. But I do believe this is factorable. I think x plus 2 times x plus 3 should do it. Always do a check. First times first is first, last times last is last, and the most important check, the one most people skip and therefore miss many of these, the outer product, which is 3x, and the inner product, which is 2x, add up to the middle term. Make sure you don't skip that check. So now we're going to apply the zero factor property. So we get x plus 2 equals 0, so x equals -2, or x plus 3 equals 0, so x equals -3. Now, for some reason I set this up on the left side, makes no difference. So we're going to properly present the x-intercepts now. We're going to say the x-intercepts are -2, 0 and -3, 0. All right, so this is all part A. For part B, we were asked to see if these result, the fact that we have two x-intercepts, agrees with the discriminant check, and that means this happens when the discriminant is positive. So when we look at our original equation, y equals, or function, y equals x squared plus 5x plus 6, we can see that a is 1, b is 5, and c is 6. So b squared, capital D, which is what stands for the discriminant, which is b squared minus 4ac, is going to be 5 squared minus 4 times 1 times 6. So that's 25 minus 24, which is 1. And we can see that that's greater than 0. Therefore, we should have 2 x-intercepts. So the result does indeed agree with the discriminant check. Lastly, we were asked to go ahead and visually display the results on a graphing calculator. So you can bring yours up if you have one, or I can go ahead and bring up Desmos in 1 second. Okay, so here we're going to go ahead and graph y equals x squared plus 5x plus 6, and as you can see visually right here, we have our 2 points of intersection with the x-axis right there at -2, 0 and -3, 0, which we already found algebraically. All right, so that's our final check on that problem, and it checked out. So we'll move on to another problem now. All right, the process of completing the square in order to take an equation or a quadratic function given here in standard form and putting it into vertex form is a fantastic process and a very, very good exercise that we should all be familiar with and know how to do. And in fact, many problems in assignments are going to require the utilization of that method. But just like before when we were solving equations, using the method of completing the square. We got to the point where we realized it would be nice if we had a shortcut so that the process can be bypassed and we can get to the result we want a little bit more quickly. And this is precisely the equivalent of that for finding the vertex of a parabola. And a lot of the work that we do here is going to look like what we did to derive the quadratic formula. So what we're going to do is, instead of taking different equations like functions like the ones we've seen earlier in the video, like the one which had a was 1, and then we did one where a was -3, etc. Why don't we just do it completely in a general manner for this quadratic function in standard form and see what happens? And that's exactly what we do. So everything we did previously with, for example, the -3, we had to divide it off and everything. We're going to do that now with this most general case. So we'll go ahead and divide both sides by a to make the coefficient of the x squared 1, and we end up with y over a equals x squared plus b over ax plus c over a. Now we're going to go ahead and complete the square, so we need to take half of this coefficient. That means multiply it by 1/2, so we get b over 2a. So we need to add that, and remember we subtracted right away. We don't forget the plus c over a, which was already there. So these three, of course, we have just created a perfect square trinomial. Those are going to turn into x plus b over 2a quantity squared, or I should say quantity x plus b over a squared minus b squared over 4a squared. That's just squaring that, plus c over a. So continuing with the simplifying, we get y over a equals, that's just a repeat of that for some reason. I wrote it twice. And here what we did was we wanted a common denominator of 4a squared. So I went ahead and multiplied this and both of these by 4a, because we want to multiply whatever we multiply the denominator by on the numerator as well. So we end up with this, and notice that we can combine those now because they are like terms. And I went ahead and wrote the positive one first, then I put the -1, just because it looks nicer, no other reason. So notice now I can go ahead and multiply both sides by a. So if I do that, watch what happens. So we have times a, here we're going to get times a, and then here we're going to get times a. But notice here, this a and this a squared will just leave you a. So that's why this expression became this. Instead of the 4a squared, we now have 4a, because we're basically multiplying the a on both sides. So we end up with y equals a times x plus b over 2a in parentheses, or quantity x plus b over 2a squared, plus 4ac minus b squared over 4a, which we can write as a times x minus, notice I wanted to write this as a difference because I wanted to see what h is going to be. So when you do that, you need a negative b over 2a here. So plus all of that. Now, this tells me that this is going to be h and this is going to be k. Now, that's a lot to try to remember. I don't need to worry about that. I went through all this process just for this. I wanted to know, if I start with a quadratic function in standard form and go through this whole process of completing the square, what is it that this h value going to be? Because if I have h, that's all I need. Once I have h, I can just plug it into here and I can get the k anyway. So there's no need for me to memorize this rather complex looking thing. So all I need is this, and that's going to help me. So given a quadratic function in standard form, in order to find the x value of the vertex, which we call h, all you need to do is divide negative b by 2a, and we'll utilize that in a second in the next screen. Make sure you can follow this, and being able to carry out a derivation like this is one of the best things you can do for yourself if you really want to improve in mathematics. So make sure you don't skip over these and say, oh, I don't need to do this, because this is how you're going to gain mathematical muscle. Okay, so here's a problem where we're asked to find the vertex of this parabola represented by this quadratic function without putting it in vertex form. So obviously we're going to be using this shortcut which we just learned. We know that the x value of the vertex which we normally refer to as h is going to be negative b over 2a. Let's go ahead and extract a and b. Notice we don't need c here. We just need to know what the coefficient of the x squared is and the coefficient of the x term is. We notice the coefficient of x squared is negative 1, and the coefficient of the x term is 5. That's b. So the x value of the vertex here, or h, is going to be negative b, which is 5 over 2 times negative 1, 2a. So notice if you simplify that, that's just 5/2. Now you don't want to stop here, because they didn't ask you for just the x value of the vertex or the x coordinate or h. They wanted the entire vertex. That means now we can take this, we can plug it into that complex looking formula from the last screen, or better yet, we can just take this and plug it in for x, and we'll find out what the y value of the vertex is going to be. So the y value of the vertex is just going to be the function defined for or at this particular x value. So we're going to get negative quantity 5/2 squared plus 5 times 5/2 plus 5. So we're going to get negative remember that that negative is not being squared, so it's going to carry. So 25 over 4 plus 25 over 2 plus 5 over 1. And of course we can go ahead and find the common denominator of 4, so that means we're going to have to multiply this by 2 and the same there, and this one by 4 and the same on the top. So we end up with negative 25 plus 50 plus 20 all over 4. So 50 minus 25 we know is 25, plus 20 will give us 45 over 4. So we can see that the vertex here is going to be at, first we put the x value of the vertex, which is 5/2, and then the y value, which we know is 45 over 4. And there we have found the vertex without having to go through the process of completing the square. Make sure you can manage this simple process on your own before we proceed. All right, so next we want to take a look at left, right, or also called horizontal parabolas. Basically, if instead of starting with y equals ax squared plus bx plus c, or in vertex form y equals a times x minus h squared plus k, if you basically switch up x and y, if you know, wherever you see y, replace it with x, wherever you see x, replace it with y, you end up with two equations that kind of, or functions, well, let's go with equations because these actually end up not being functions, as you'll see. Here's a graph of one. Notice to be a function, the graph of a relation has to pass the vertical line test, and notice this one fails badly. There are many vertical lines that cross these more than once. So the up-down parabolas that we've been discussing, and which are the most prevalent and the most important, are precisely so because they are functions. Notice that if you look at the graph of a up-down parabola, let me bring one up real quickly just for reference. So here's the reference parabola itself. Notice y equals x squared. No vertical line will cross this graph more than once, so this does pass the vertical line test, as will all parabolas, even the ones that are shifted, etc. So all of them are functions. But when we look at a horizontal version, so if we switch x and y and graph x equals y squared, notice these no longer pass the vertical line test, so these would not be functions. However, they do play a role sometimes and are important to understand, so we'll go ahead and cover them for the sake of completeness, if for no other reason. So a few things to notice is, first of all, notice that the axis of symmetry is not going to be vertical. Obviously, it's going to be horizontal. So it's going to have the form not x equals h, but rather y equals k. Now, h is, when it comes to associations, h always goes with the x and k will always go with the y. Now, even in this form, hk is still going to be your vertex. Everything you've learned basically works, just turn it around and make it horizontal. A greater than 0 when it comes to up-down parabolas means it opens up. A less than 0 means it opens down. With left-right parabolas, a greater than 0 actually means it opens to the right. A less than 0 means it opens to the left. Now, the standard parabola for these types of parabola, the left-right ones, is not y equals x squared, but x equals y squared. So you can see a symmetry between everything we've done and everything that works with these left-right parabolas. Now, when we were graphing these, remember we always found the vertex first, then we looked at a point to the left and a point to the right. So with these, obviously, you're going to look at a point below and a point above the y value of the vertex, not the x values. Okay, so given all that in mind, we'll go ahead and look at a graph now. So here we have a relation of the type we just discussed. We have to be very careful not to call these functions because they're not functions. So if it looks familiar, is because it is. Let me remind you. Remember the first example we did earlier? I have taken exactly this example and I've changed x and y. So instead of y equals x squared plus 6x plus 11, we're looking at x equals y squared plus 6y plus 11. I did that because I wanted you to see how similar the procedure is. We do exactly what we did, except we don't switch f of x with y or anything like that because we don't have an f of x. There's no function here. So we just go ahead and make sure the coefficient of y squared is 1. Proceed with completing the square just like before and put it in vertex form. Now we go ahead and set this equal to 0. That gives us y equals -3. See? We start here on this side with the y, then we go 1 below. Notice, what's 1 below -3? -4. And we go 1 above, so that's -2. Then we go ahead and compute these, which is easy. Plug in -3 for y, you get 0 squared is 0 plus 2. That's where this 2 comes from. Then plug in -4, you get -4 plus 3 is -1 squared is 1 plus 2 is 3. Do the same for both -2 and -4 and you should get 3's. Make sure you do both, don't just settle for one. So now we can see this is k is going to be the opposite of that, which is -3, and this is going to be h. So the vertex is at, remember, be careful here, don't put kh, it's still hk. So 2, -3 is the vertex. The axis of symmetry is this horizontal line, which is actually y equals k. So y equals 2 in this case. Pardon me, k. See how easy it is to make that error. K is -3, so y equals -3. Remember, x equals 2 is up here, so we don't want that. We want this horizontal line, which is y equals -3. Now, even though it's not a function, you can still talk about domain and range. That just means the set of all the x values that are in play and the y values that are in play to provide this graph. Notice the domain would be basically all the x values from here onward. So it'll be bracket 2 comma infinity, and the range this time, notice all y values are in play. So the range is actually -infinity to infinity, or all real numbers. So notice everything works out the same way. You just have to kind of shift your mind around to where you do things in a horizontal fashion rather than a vertical one. Notice that a here is 1, so it is just as wide as the reference parabola x equals y squared, which is, of course, if you take it and turn it 90 degrees to the left, is just as wide as y equals x squared itself. So anyway, that's how you handle those, and we're going to just look at a couple of quick applications and we'll be done for the day. All right, so your favorite word applications, which of course means a couple of word problems. So let's go ahead and take a look at one. Here we have an application where we want to find a pair of numbers whose sum is 100 and whose product is maximum. So this is the kind of problem we call an optimization problem. Basically, we have two numbers, so we'll go ahead and give them some names. So let's let them be x and y. So that means we want x plus y to be 100, the sum. And we want their product to be maximum. That's kind of a strange thing. We haven't dealt with that before. So here's what we'll do. We'll just create a function p of x, y, and we'll just let it be the product. So that's going to be x times y. Now, in these kinds of optimization problems, since this is the quantity we're trying to optimize, maximize, we call this the objective. And since this is the kind of constraint we have to deal with, this is like puts a limit on, because if you just wanted two numbers whose product is maximum, hey, who's to hold you from going for larger and larger numbers? But remember, you're doing this within the boundaries of this constraint. So that's why this equation is called precisely the constraint. All right, so the goal here is hopefully to deal with just one variable, and that's very easy to do here because we can go ahead and take the constraint and solve it for y, for instance. Y equals 100 minus x. Now we can take this and substitute it for y in our function. So now instead of saying p of x, y, I can just say p of x, because now I'm just going to have one variable. So I get x times 100 minus x. So basically I'm trying to find the x value that makes this function maximize. Now if I go ahead and multiply that out, I notice that I get 100x minus x squared, and I go, oh look, that's a quadratic function. So I'm trying to find the maximum value of a quadratic function, or at least I'm trying to find the x value that gives me that. So think about it with a quadratic function, and notice if I write it in actual standard form, it becomes negative x squared plus 100x. So notice this is a quadratic form with a negative a. That means this is a quadratic form that's going to have a function looking like that. So it's an upside down parabola which will have a maximum point. So and you know where that happens at the vertex. So all we have to do is find the vertex of this quadratic function, and we'll have the x value. Once we have x, we can plug it in here and get y. Then we'll know the two numbers whose sum is 100 but whose product is maximum. So now we can find the vertex by putting this in vertex form, or we can simply just use the shortcut which we just learned. But let's go with the shortcuts just to get some practice with that, since we've done a few of the other type. So here we have a equals -1, b equals 100. So we know that the x value of the vertex is going to be -b over 2a. So we know it's going to be -100 over 2 times -1. That's 100 over 2, which is 50. Now if x is 50, that means y, notice y is 100 minus x. So y is going to be 100 minus 50, which is also 50. So this is very interesting, because what we've just found, so here now we can say the numbers are 50 and 50. So what we have just found is that of all the numbers that you can take and add together to get 100, the two numbers that will give you the maximum possible product are 50 and 50. So think about it. You can try any combination you want. Like let's say take 80 and 20. That would give you a product of what? 1600. Take 90 and 10. That'll give you what? 900. Take 60 and 40. You're getting closer, right? You get 2400. But notice this, 50 times 50 is 2500. So of all the possible pairs of numbers whose sum is 100, the two which are going to give you the maximum possible product are 50 and 50 when they're equal. So that's a nice problem. It shows you the power of parabolas and the kind of application you can get out of them. Anyway, so make sure you understand that, and we'll look at one more example before we call it the day. All right, so for our last problem, we're looking at a baseball which is being shot straight up like this. Of course, think about it. If you're shooting a ball straight up, what's it gonna do? It's gonna go up. It's not gonna go up forever unless you've given it such a massive shot that it's gonna escape uh, Earth's atmosphere and just keep going, right? So that's called escape velocity. So as long as it's just a regular kind of initial speed or initial force that you're applying to it, it's going to go up for a certain time, right? And then it's going to stop and it's going to drop back down. So when they say to you that this gives you the height at any time t after the initial uh, start, it's not telling you that this ball is going to have a parabolic path that you see here. Here, I've graphed this just to give you a visual. You don't need to do this graph to be able to solve this problem. What this is giving you, this graph, is the height of this ball after t seconds. So notice the height is going to increase while it's going on its way up, then it's going to hit a maximum height. Then what's it going to do? So it's going to go reach its maximum value, then it's going to drop back down, right? So the path is straight, it's not curved, but the time is being displayed here and its relationship to the height. So after a certain number of seconds, it'll be at a certain elevation. That's what this graph is showing you, the relationship between time passed in seconds and the height of the ball in feet. So again, if we find this vertex, we'll know the maximum height that this ball will reach because we have the perfect image of the various heights this ball reaches according to this quadratic function here. So all we have to do again is to find the maximum value of that function. That'll give us how many seconds it's going to take to reach that height. Once we know the number of seconds, we can plug it in here and we'll know the actual height, because remember, s of t here is giving you the height after t seconds. So again, we can use our x value of the vertex equals negative b over 2a formula. So we get, notice that a is negative 16 and b is 32. So we get negative 32 over 2 times negative 16. And notice this is going to be 32 over 32, which is 1. So now, remember this here, I should say, actually, since we're given t versus height, it's better to use t here. So this is going to be a time that we are finding here. So we're going to get 1. So now we want s of 1. So that ball is going to reach its maximum height in actually just 1 second. So it's a quick flight. So we're going to get negative 16 times 1 squared plus 32 times 1. Notice that's going to be negative 16 plus 32, which is 16. So this ball, from the time that it leaves till the time that it reaches its height, takes only 1 second, and by the time it reaches that, it has reached a height of 16 feet in that 1 second. So the answer here will be, what is the maximum height this ball will reach? 16 feet. So there's another application utilizing quadratic functions. And that should be enough for this video. So make sure that you practice and be safe until we meet again.